Alright, let's get started with our first problem of the day, which is path sum 2. So, given the root of a binary tree and an integer target sum, return all root to leaf paths where the sum of the node values in the path equals target sum. Each path should be returned as a list of the node values, not node references. A root to leaf path is a path starting from the root and ending at any leaf node. A leaf is a node with no children. Okay. Interesting. Funnily enough, I think this was a problem that someone asked on the CS Careers Discord server yesterday. Let's see. I think they mentioned something about like use path sum 1 but on every node. No, but you need to start at the root and end at the leaf. Let's see. So probably a recursive solution. We could do like a in order traversal until leaves. The parameters will be root, which is tree node, a target sum, which is an int, a current sum, which is an int, and we'll return int, return list int, or maybe reference unit and reference. And what I mean by that is that maybe we pass in the list as a mutable list reference, and then we return that instead. And let's see. So suppose that we are at a given root R. If root has leaves, traverse down those leaves on the left and right, or has children, rather. We don't know if those are leaves. Traverse down those children on the left and right. If root does not have children, if the root, if the current sum plus root is equal to target sum, add current sum into the list and return so, or not add current sum, add our root.val into the list and return. So what that will do is that it will add we can say create a left list for the left child, right list for right child. See if they populate with anything. Otherwise, return an empty list. The problem is that this can create 2 to the n lists, which is a little bit awkward. It doesn't feel like that is correct. And I'm not gonna lie, it feels like it's been a while if I have done path sum. I don't remember what path sum 1 was. If we create 2 to the n lists, that's a lot of lists to hold references to, which kind of seems to not be a thing. What if instead of creating what we do is return a list with root val inside? If the child list returned is not empty, then add current root val and return that list. So the idea then is that each node can create a list, and thus we reduce our list size to O of n, because at most each node can create a list that is returned. So I think we're leaning towards the list int return. Well, probably list int, right? Because if we have we need list int, because if both sides of the tree rooted at root can have a sum, then we need to return both. Right, so for here we need to have a return of both lists, so we wrap the lists inside another list. And I think this works. I think this seems to do fine. This is just pure traversal. That is just, and then at the end, we need to go through each list and reverse them, because the way that they are returned is in the order of is in the order from the leaf to the root, but we want the path from the root to the leaf, right? Or we could consider, do we really want to create the list at the root before we know? Well, we also have a couple of things, like if current sum plus root dot val is greater than target sum, we don't even need to bother checking the rest of the tree, purely because then there's no way that we can include our current root as a value within the path, and therefore we should just back up. We should also do if the root is null, then we also return an empty list. We can create 2 lists here, but at the same time, what we could do is that if there are children, then for each child we create the list with our value included. And and we pass that by, but then we'd have to include that by reference down the chain. So, we could do that. We could pass it in by reference. But then we'd have to create up to two copies of it every time. So here, we pass 2 copies of 5. We pass 2 copies of 5, 5, 8 into these. And then we pass 2 copies of 5, 8, 4 here, and here. So I'm not sure if that would be efficient on the space side of things. I think there's a time and space trade-off. So exchanging space for time, pass in a duplicated list by reference and append to that, requires up to O of, well, would it be O of 2 to the n? If we had O of n nodes, right, then we'd create one list here, or 2 lists here, 2 lists here, 2 lists here. So that'd be 6 in total, which isn't bad, I don't think. Let me think. Time and space complexity is always the annoying part of it. We create 2 per node. No, actually I think that would still be fine. I think this is still in the realm of O of n, actually, now that I think about it. So if that requires up to O of n space for the lists, then that seems to make sense. So we can say current path, which is a list of int. So what we do is that we pass in a list int. We want to pass in the current sum so we don't have to keep on running this path and reducing it. And then this path will end up being encapsulated within a list of these int lists when we send it back up, in case both of the branching paths that exist within this subtree contain a viable path. Okay. But in that case, how do we verify that a path actually works, right? Well, in that case, if we don't find a list that works for us, then we could just return an empty list, right? If we return an empty list, then we can still verify that, okay, that path didn't work, and so we don't consider it. Interesting. This feels almost like a backtracking problem, where we kind of want to like explore each individual path, see if it works, and if it doesn't, then we just return an empty list, and that's like sort of our constraint. We want the values to equal our target sum. Okay. I think this current path idea would work. And the reason why we'd want to do this is that so by passing in the list rather than creating it from the bottom up, we remove the need to reverse each list after we return, right? So I think this makes sense. And this will take O of n time O of n space, where n is the number of nodes within our tree. And I think with that, we can get started coding. So let's take our root, which is a tree node nullable, a target sum, which is an integer, a current sum, which is also an integer, and a current path, which is a list of integers, which and then this function as a whole returns a list of list integers. This is path sum, not path sun. And we know that if our if root is null, then we return an empty list of list int. We could also do if root is if current sum plus root dot val is greater than our target sum, then we also want to return it, because there's no way that we can progress further from here, from this point, including our current root. So there's no point in checking the other items. And this only works, now that I actually read the constraints, and this is a mistake on my part now, we have the possibility of having negative values. Well, actually, yeah, you're right. Okay. In terms of having this constraint only can hold if our current sum, or if each root value can be only at least 0. Because then we have a guarantee that if we go further down the tree, then there will never be a possibility for us to decrease our current sum to the point where it meets target sum. However, there is a constraint within this problem that the node value is at minimum negative 1,000, and thus there is no guarantee that we won't hit a perfect summation in which our current sum would be initially greater than our target sum and then go back down to our target sum. So we can remove this constraint and we can continue on. So then we have to really consider all of the paths, essentially, because we have the possibility of a negative value within our node. So let's do this. If root dot left is not null, if root dot right is not null, if root dot left is null and root dot right is null, so leaf node, and we don't want to separate this into an if or else if case, because we want both of these to actually run if they are true. If the left is null, we want to get the path at the left side. If the right side is null, we also want to do that. So we can say val left result is equal to running a path sum at root.left with a target sum of our own target sum. Our current sum will be adding to our root.val, and our current path will add our root.val. And pretty much a very similar thing for our right side, except that this will be going to our root.right, and this should be renamed to right result. So if left result is not empty, and we can create a val return list is a mutable list of list int, then we can say return list dot add our current path plus root dot val. And very similar thing on our right side. That if our right result is not empty, which means that we found a path, then we want to add to our return list actually we can just do return list then left result for each list return list dot add list. Because the idea is that we want to essentially unzip this so that we get all the lists, all the paths within here, and we add it to our return list. Okay, so that's dealing with the left and the right results. And now we consider our root node, our leaf nodes, and we say that if current sum plus root.val is exactly equal to our target sum, then we will say return a list of a list of list int with one value, which is going to be our current path plus root dot val. Otherwise, return empty list of list int, and beyond that, we return our return list. Actually, we could just get rid of this because this list will remain empty, and we can sort of reduce this to one line. So if our current sum plus our value is exactly equal to our target sum, then we can return it. Let's see. So let's double check first our inner value. So if our root is null, we return an empty list. Yep. If our return list, we initialize a return list, which is a mutable list of paths. If our left child is not null, we will iterate on the left side. So this is more like post-order traversal, to a certain extent, right? We grab our list, or we iterate on the left side with the same target sum. The target sum does not change. The current sum is our current sum plus root val. Let's see. We could also consider changing it so this target sum actually is not static. And what we do is that we change it so our target sum essentially minus root.val. So the idea is that our target sum, once we visit a node, so let's say that our target sum is 22. We see this 5. Well, then our target sum here is 22 minus 5. And then we continue, and then we continue, right? So 22 minus 5, that's 17. 17 minus 4, that's 13. 13 minus 11, that's 2. And 2 is here for the target sum. So now we can actually get rid of current sum altogether as an attribute, or as a parameter to our function. We don't need it, and that saves us a little bit of calculation time. Not significantly, not asymptotically, but it's still nice. And now our target sum that we actually pass in is our original target sum minus our current value. Of course, if this is a negative value, this will also work because, for example, if this was -5, then 22 minus -5 is 27. And of course, we want our sum at the path here for the remaining part of the path to equal to that 27 in order to offset the -5 if it were here, in order to get our target sum of 22. So that all works out. So let's see. So let's go back to this. So we have our target sum, and then we also pass in a list. This is a non-mutable list, which takes our current path and adds our root val to it. If this result is not empty, which means that a valid path was found, then we will take each remaining path that that exists from this and return it, and add it to our return list, essentially. So for here, for example, this 5, we'll pass in a list of 5. This 4 here will pass down a list of 5, 4. This will pass in a 5, 4, 11. And this 2, once this adds in, will return a list of a path, which includes 5, 4, 11, and 2. This will be added into, or this will be returned as a list. So this will be returned up. And here, this list, this path, we just add it to our return list, and then we return. Add it to our return list and return. Add it to our return list and return. So that logic seems to be relatively sound. Of course, now we check, after the subtrees, we check our node to see if it is a leaf node. We could also check this above, right? And this would maybe marginally speed it up. And we could actually do this even before calculating our return list, because it's not here. So it's not used in the leaf node calculation. So we can do this first, and that way we don't have to run this expensive sort of list initialization and all that overhead. We can immediately return else return empty list of int. Maybe a little bit awkward here, but no additional calculations at the leaf level in this case then. So if we reach a target sum with our value, and it is a leaf node, which is implied by the fact that this if statement is within the other, then we can return our path, including our current value. Otherwise, we just return an empty list, and we know from the left and right subpaths or subtrees that if an empty list happens to show up, then we just don't consider it at all. And at the end, we return our return list. So let's go ahead and also write this call here now. So we'll do return path sum in our main function. We'll do a root, which is the same root, our target sum, which is our target sum. And our current path will just be an empty list of ints. Is it just empty list or empty list of? I always forget. Usually don't do empty list, so. It's just empty list, okay. So that is our initial call. We go in with an empty list on our root with our initial target sum. And this is what kicks off pretty much the entire exploration. So running through this example here, we start with 5, recurse on 4, recurse on 8, with target 17, as we said. current path 5. This 4 recurse on 11 with target 13, current path 4, or 5 comma 4. So this, it's not null. The root is not null. Left and right are not both null. So we create this empty list. Left is not null. So we go through here. And we check from our current path, add our root to it, target sum, which is the difference, and we continue on. Same thing with 4. We do this, not null. Not both subtrees are null. It's not a leaf. We continue. Left side is not null, so we recurse on the 11 with a difference of 13, and we add our current node into our path. This will first recurse on 7 with target 2, current path 5, 4, 11. This returns nothing, or returns empty because 7 is leaf and not equals to 2. Recursing on 2 with target 2, however, current path becomes 5, 4, 11. And this, because it's a leaf and the value is a target sum, we return a list of list int, which has one value, which is our current path, 5, 4, 11, plus 2. This might require me to wrap it in a list. Hopefully it doesn't. So that returns up to 11, then 4, then 5. So this goes to 11, and now 11 is done. Add that to our return list, return. Add that to our return list, return. Up to 5. Now we recurse on 8 with target 17, current path 5. Recurse on 13, our left side first, with target 9, current path 5, 8. This returns empty because 13 is a leaf and not equal to 9. Then we recurse on 4 with target 9, sorry. Current path is 5, 8, and 4. Then this recurse on 5 with target 5. Current path is 5, 8, 4. This returns this because it's the same as the target. So 5, 8, 4 plus 5 returns up. And then we recurse on 1 with target 5. Returns empty. 1 is leaf and not equal to 5. And then this all returns up all the way until 5, which then aggregates both the left and the right trees, the left and right subtrees, and then passes it back up. And then we get our final answer, which is 5, 4, 11, and 2, and 5, 8, 4, and 5. So this seems to work, barring any compiling issues. So let's go ahead and run this code. And let's see if there are any issues with the compilation first. Looks like, oh, this should be a list int, not a list. Okay, looks like it seems to work for the first example. Let's go ahead and run the second and third examples. Looks like they seem to work as well. Let's go ahead and throw in a submit. And it seems to be accepted, but it is a little bit on the slow side. Now, where is the slowness coming from? Well, we know that adding to the end of a list, which is what we're doing here, here, and here, is relatively slow. So what we could consider is, rather than using a list here, we could use a linked list here, and that might be a little bit faster, because then adding to the end of the linked list is not adding to the end of a linked list is not going to be O of n time on average, where n is the length of the list. But that will also interfere with this, and I'm not sure if this list and this linked list will play nicely together. I have a feeling that it won't. And in that case, we'd have to convert the linked list into a list anyways. Right. So we'll have to convert it into a linked list, or the list into a linked list anyways. And in that case, I don't think there's really anything special about the list, or anything about it, because when we convert the linked list into a list, we'll have to iterate through every element anyways. Though, at the same time, we do save on a little bit, I think. Let me think. If we really wanted to do that, so it's mainly just here, right? Yeah, and some other spots. Okay. Let's see if we can make this work. Let's see if we can make it work, at least. So this doesn't need to change. Let's see. This doesn't need to exist there. So we can create a new list. Is going to be a mutable list of int, and then we can say current path dot add root dot val, and then current path for each item. We do new list dot add item, and then we can just add it within this new list here. And we can do here, we can do dot add. Well, but then if we pass in a linked list, right, then we need to copy the items over anyways. So I'm starting to wonder if there's really any reason to do this. Because we need to create a copy of that list, right? So we can say val left input is equal to linked list of int, which is just going to be a copy of current path. And we can say val right input is a linked list of int that'll copy the current path. And I'm not even sure if if this is legal to just use this way as a copy. Let's see. Oh. Left input dot add root val. And then we can write, this would be right input. And do right input dot add root val. Because then we're still copying the items over. And this is just linked list. I do wonder if this is faster at all then. Because we still have to copy the items over. We still have to copy the items over from the linked list. It's not like it's like necessarily any faster in that case. I don't know, we'll see. But LeetCode can be weird, but I think ultimately this doesn't really affect our asymptotic runtime, right? Yeah, and it's slower. It happens. In any case, that's not a really big implementation detail in either way. Anyways, so the idea is that we create our path. If we have a left and right child, we'll pass our path down and we'll see if we can get to our target sum. And if it does, then we'll pass back up that path. Otherwise, we just pass back an empty list. And then we sort of aggregate that all together. And then we pass that and return that all the way up. I hope you learned something, and I'll see you for the next problem.